All right. Yeah, hi everyone. Yeah, Yogi has raised a hand. Yeah, please. Okay. That is tomorrow. Okay. Uh, right. So you wanted to have the class sometime else in the week or something like that? Okay. Mm-hmm. So 14th, what is the time deadline time? End of the day, right? 12 afternoon tomorrow. Night, right? Yeah, so you will get a whole day, right, to do the assignment. And the assignments are pretty easy. Like I mean, if you spend like half an hour, it will be done. And I think it is actually, you know, most of you, I guess, do the assignments at the last moment. So in the last moment, if you are like, and you can start your assignment early as well, right? You don't have to wait for my lecture for the assignments. And let's say you are able to solve 8 questions by yourself and you're stuck in two, right? So you can ask me during my session that, okay, these are the 2 questions in which we're having trouble. Then we can go in detail into those questions. Or like, even if you are, if you haven't solved the assignments, I think if you attend my lectures, you can solve them in like half an hour, hardly. Like I saw the assignments, week 3 assignments, and if you just attend this lecture, you can like solve all the questions in within half an hour. It won't take you much time. So like if I take my session very early in the week, then people generally solve the assignments towards the last hour and they will almost forget everything what I've taught. So I think this time is I think will be good as well, right? Is that fine? Because like it will be difficult for me to change the timing of the class. Yeah. Yeah, thank you for understanding. Yeah, Veer is asking, is linear algebra a prerequisite for this course? Uh, you know, not really. Not it's not a prerequisite for this course. But if you want to learn it, it's good. If you want to learn it, you will find some applications of linear algebra. So I mean, in my lectures, I'll try to not go uh, into the mathematical intricacies of the topics. I'll try to explain it you know from a machine learning perspective, which do not require any mathematical background from an analytical perspective. But if you know linear algebra, if you know probability and statistics, I think you'll have a different perspective as well. It will help you understand some concepts uh, from a mathematical perspective as well. So it will be beneficial for you. But yeah, if you don't know, it's fine. It's fine. Right. In the previous 2 lectures, I didn't talk about anything in with much mathematical rigor, but it can be done. But if you're not familiar with the concepts, it's fine. Mm, yeah, you joined the course a little. Vedika is saying you joined the course a little late, so I missed out on assignment one. Is it fine? Yeah, so if you have missed out on assignment one, I think you will be graded. You will not be graded on that assignment. In that case, you can, mail the NPTEL, respective. person to NPTEL and telling them that you can if you can get a extension on your assignment, right? So maybe then maybe they will allow, or yeah, uh, I'm not sure about that. So as I was telling, like my session is, uh, will be very helpful if you attend this session. It will be very helpful for you to solve the assignments and you know um, get a conceptual understanding as well. And here you can ask questions and doubts and everything. And finally, like I think every one of you are attending this course because you want to do something like you want to pursue your career in this field, right? So I will also try to give you enough hands-on during the session, and I'll also share the notebooks as I did for the last week, so that you can play around with those notebooks and get more insights from the hands-on exercises. So that will be beneficial for you as well in your future if you are planning a career in this. And because in the industry or wherever you go, I mean, you ultimately have to um, do this, build these models, and test this and validate this and do those things. So hands-on in machine learning is uh, is required, right? And also, as I said, like if you uh, haven't attended the lectures, if you didn't get the time to go through the lectures by the professor, no worries. I mean, I will summarize them again in this TA session. So in this TA session, basically, as you can see, like those who have attended week 1 and week 2, they will see like, these have been structured such that, first I will talk about the theory concept, summarize them. Then I will talk about some numerical problems, how to solve them. And then I will talk about, I'll show some hands-on exercises as well. And so these actually do three tasks simultaneously, right? So basically, as I said, theory, numericals, and hands-on, right? So yeah, this will be, I think, beneficial for you for solving the assignments now, and as well as uh, if you are, pursuing your career in future in this field. So yeah, let me share my screen. Yeah. Is there any further questions from previous weeks? Yeah, good evening. Okay. Well, Shreyosri, right? Okay. So, did you see my week 2 lecture? Okay, okay, okay. So, yeah, so if you can go through my week 2 lecture, I've explicitly, called for a yeah. Mhm. Mhm. Right, 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 right. Yeah, I do actually. Actually, if you see week 2, I've explicitly solved, I've written down all the steps and solved for a real decision tree. How to, get the value of entropy and, information gain and all those parameters. So if you just, go back and, just go to the lecture, And you will see, like for a particular tree, I have solved for the entropy in each of the nodes. And then after calculating the entropy, I have solved like what are the information gain for each of the splits that we make in the decision tree. I think it will be very helpful for you. I think it will clarify the math and, okay, okay, fine. So let's start without, over more time. So let me yeah, so my name is Rohan. I'm a PMR TA. I'm from Indian Institute of Science, Bangalore. And yeah, so let's start with that. Okay, so in this week, we will cover basically, more or less four algorithms, I will say. One is the K nearest neighbor, KNN algorithm. Then I will move on to PCA, principal component analysis, and LDA, linear discriminant analysis. And finally, we'll talk about recommended systems, right? So start with the first part, that is k nearest neighbor. Okay. So so this is a representation of your data basically. So let's say you have some data which has some x values and y values, right? So let's say um, you're trying to classify so you're doing a biological experiment and you are checking that what is the so you have some set of mices, right? So you have some mice, and among those mice you are trying to see, like you are given data about the two genes of that of all the mice. Okay, so let's say gene 1 and gene 2 data you have, right? So and you're trying to classify them, that whether if any of the gene is making them obese or not. Let's say obesity of mouses, right? Mice. So basically, class B, the green class. Let's say these are the classes of mice which are obese, and the red class is the classes of mice which are not obese, right? So on the x-axis you plot gene 1, on the y-axis you plot gene 2, right? So class A, as I said, is not obese. So what does each of the data point means, right? So this is the, let's say x-axis is the value of gene 1. So gene 1 value is this, okay? For this point, for this mice, let's say this is one mice. So for this mice, gene 1 value is this, and gene 2 value is this, whatever is in the y-axis. And similarly for all the other mice, okay? Now, you see the green class, as I said, is the classes of mice which are obese. So, so you can like, get an idea by visual inspection that, the classes which have higher percentage of gene 1 and, lower percentage of gene 2, these are making the mice obese, right? On the other hand, the mice which have lower percentage of gene 1, whereas higher percentage of gene 2, they are not making them obese, right? So this could be one of the, practical examples that we see. Okay. Now, is that clear? Okay. So, feel free to stop me whenever you have a question or something. Okay, so this is your data, right? So you have plotted your data in x and y axis, and you are just getting visual inspection for it. Now, now what happens is that you are given a data for another new mice. Okay, let's say some other mice which was not present earlier in your data, right? So now you're given the data that okay, this mice has this percentage of gene 1, this percentage of gene 2, right? And you have to predict whether that mice would be obese or not. That is your problem statement, right? So what you do is that you know what is the percentage of gene 1 in that mice and percentage of gene 2 in that mice. So you again plot the value of gene 1 and gene 2, and you plot the position in that xy plane, and this is what your position is. This is the new example that you get. Okay, now you have to classify this example, and you have to classify whether this mouse will be obese or not, whether this mouse will fall in class A or class B, right? So this is your problem statement. Now what you do is you calculate uh, the distance of each of these uh, mice from this new mouse. Okay, so let's say distance of this new mouse from this green one is something, let's say 1. And I'll come to what I mean by distance actually. Okay, I'll come to that. So but let's say this distance is 1, this distance is, let's say, 1.5, this is even further. So this distance will be, you know, 2, and this distance is even further, let's say 3, and so on, right? So distance is basically, what you physically see, right? Distance from one point to another point, right? So how do you calculate the distance from one point to another point, right? So in Euclidean plane, if we have some if you can have, if you have 2 points whose coordinates are, let's say, x1 y1, and another point has coordinate x2 y2, so the Euclidean distance between them is x1 square, x1 minus x2 whole square plus y1 minus y2 whole square, right? That is the Euclidean distance. That is basically the what you call the distance between the 2 points, right? If you take a measuring tape and you measure the distance between the 2 points, that is what you get, right? That is the Euclidean distance, right? So this is the distance measure. This is actually the formula. So in 2D plane, that's what the formula you use: x1 minus x2 whole square plus y1 minus y2 whole square. But in a n-dimensional plane, so this data is very simplified, because we have only two dimensions to this data. But if you have, like, gene 1, gene 2, gene 3, and so on, 100 genes, let's say, so you have to get an idea of how to get the distance for that 100 dimensional data, right? You cannot plot a 100 dimensional graph, so there should be some way to you know uh, measure the distance between 2 points in a n-dimensional manifold, right? So this is the measure of distance. So this is summation of ai minus bi whole square by some normalization constant ri square. So this is the range of the ith component. So this is how you basically you know uh, if without this Ri, this is just the Euclidean distance, right? This is just summation of ai minus bi whole square. That's what you get in case of a Euclidean distance, right? But this Ri, what is the significance of this Ri? Is this Ri is basically normalizing uh, all the parameters, right? Is that fine? Okay. So why do we require this normalization? One thing is that all these genes, gene 1, gene 2 might have different ranges, right? So let's say gene 1 has range of between 1 to 10, whereas gene 2 has range between 10 to 100, right? So since these have different ranges, we want to normalize the data so that all the uh, values are normalized to some within some fixed range, let's say 0 to 1. Okay, so that is why we do normalization. Otherwise, distances could be very over measured sometimes, because when you're taking gene 2, since the since the range is too high, that will increase the distance abnormally, right? Whereas in case of gene 1, it will not. So basically, a little separation between two genes would be magnified basically in case of gene 2, whereas it will be undermined in case of gene 1. uh, can we normalize using other statistics, like standard deviation instead of range? Yeah, of course. Yeah, we can. So yeah, there could be many ways of normalization, but the idea of normalization is basically that you want to have your data, all the features under the same range. Okay, that is the idea, so that you're not getting magnified or undermined in some of the features. So basically, you are giving equal weights to all the features, right? So that is the idea. So yeah. So after you calculate the distance to from this new example to all the other examples, you see what are the uh, nearest neighbors of this new example, right? So if the data points are, so someone is asking, Dhanya is asking, if the data points are widely separated, how do we normalize? Yeah, so no issues. So if some data points are widely separated, so basically, let's say, you have some wider separation in one of the axis. Let's say in the x-axis, your data is like separated from here to here. So there is a wide separation, right? But in the y-axis, you have relatively, you know, smaller separation, smaller width. Okay. So basically, what you do is that you can uh, you can use the this width. Okay. So what is the separation in the x-axis, and you divide that uh, using that width. So that is basically this width is basically your Ri. That is the range. Okay. So what is the range in the y-axis? X-axis is this range, this whole range, this place where you get the first uh, red point until the end point. So this is the range basically. You can see my if you can see my pointer, okay. So there is one line. I don't know if I can draw a line, but let me try. Okay. So yeah, if you see this, this is the range in the x-axis, right? So you can see the line, right? So this is basically the value of Ri, R1 basically. So in the x direction, only this x direction range is this, whereas this is the range in the y direction for the gene 2, right? So because this is the range across which these uh, values are present, right? Okay. So I hope this is clear. Okay. Okay. All right. Now, yeah, after you have, normalized your data, calculate the distance. Now, now you have to choose how many nearest neighbors you need to consider, right? You want to consider basically. So let's say you consider three neighbors, okay? So you want to say that, okay, I will consider only the nearest 3 points to my new data point, right? And I want to see what are they classified as. So if you see the smaller circle, this is the k equals to 3 circle. So these are the three nearest neighbors to this new example. So if you see among these three neighbors, two are in class B, one is in class A, right? So what you see that, okay, my nearest neighbors are in class B. So I should also be in class B, right? So if I have, I'm closer to class B than class A. So that is what you get. So you classify this example as to be in class B, right? So that is the idea, right? This is the algorithm. This is it, right? So if you have any questions, ask me now, or we'll go deeper into it. But this is what is being done in the group. This is all. Okay. Okay. Now, if let's say you want to take more neighbors, right? Instead of three, you feel that okay, three is not enough. I want to have more neighbors in to consider my classification. So what you do is you go to higher neighbors and you try to see. Let's say you take k equals to 7, right? Now you consider the seven nearest neighbors. So this is the circle within which all the seven neighbors lie. So 1, 2, 3, 4, 5, 6, 7. Okay. And out of the seven neighbors, you see that four are in class A, three are in class B. So now uh, your prediction changes. Now you see, okay, now I have four neighbors in class A, whereas three neighbors in class B. So this I must be in class A, not in B, right? So what was this? Why the difference is coming? Why if you take class k equals to 3, you are being predicted in class B, but if you take more neighbors, you're getting predicted in class A. So why is this difference coming? And what is the optimal way to choose the value of k? So you don't know like which value of k you should choose prior to in prior, right? So in prior, you just have a data, you get a new example, but you don't know which k value would give you the best result, right? So that is basically the question, how to choose the k. So I'll come to that later on. So I'll do a hands-on, Python tutorial after this. So I will explain it like how to choose the value of k and what is the best k that you should have, right? But in the meantime, you're free to come up with your answers, or your what do you think? So please let me know in the chat. Or so okay, this is a Voronoi diagram. I think so. Basically, these are the examples. So these points, if you see black dots, so these are the examples, the data points in the XY plane. And these cells, if you see the colored cells, these are the cells which define like in which is your nearest neighbor. So basically, if you are falling in this green cell, so basically your nearest neighbor would be this green dot, right? So this dot. Whereas if you are falling in this violet cell, your nearest point would be this dot. So this is just a representation to see that uh, if you have your data set like this, where if you have a new example coming in, which is the nearest neighbor to this example, and which are all the nearest possible. So this is just a representation. This is just to visualize things, but I'll come to the hands-on part where you will see like how we do it. So in the meantime, Mainak is asking, is K a hyperparameter? Yes, it is a hyperparameter. And how do we determine the values of hyperparameter? I think it was covered in class in the previous weeks. So it is by cross validation, right? So we'll see like how we do that, right? More number of neighbor A is in case equals 7, but yeah, right. V is right. That's why we classify it as class A in one case, and in class B in another case. But one thing to note is that in k equals to 3, if we are looking at lesser number of neighbors, you know intuitively, don't you feel that we are like underfitting our overfitting our model, right? So because if let's say instead of k equals to 3, even if you lower the value of k, if you take k equals to 1, then what happens, right? So you are saying that, okay, my nearest neighbor is in class A, so I'll be in class A. But you ignore all the, let's say, 10 other nearest neighbors. So if you ignore only the nearest neighbor, very nearest neighbor, first nearest neighbor, you are classified being as in class A. But if you, let's say, consider, other neighbors as well, which are not as near as the first neighbor, but, pretty much near as well. So if you consider those neighbors as well, you might be classified as class B, right? In a different class. So you have to see that, if you're lower value of k, you are kind of overfitting your data, right? So a very low value of k is also not a good idea. Right? So we'll see why is it overfitting, and so when I say overfitting, then the terminology that should come to your mind is variance. So if you have attended the previous weeks, you should know what is bias and variance, right? So the term that should come to your mind when I say overfitting is variance, right? And when I say underfitting, it's bias, right? So lower k values gives you a high variance, and a very high k values gives you uh, high bias, right? Because it is underfitting your model. You're taking into all the variables, all the data points, and you're also fitting the noise and everything. So you're kind of getting an average estimate. You're not classifying it very accurately. Right? So, okay. Now, I will talk a little bit more about the distance measure in K-NN algorithm, and then I will just go on to the hands-on. So, right now, what we saw is that this Euclidean distance measure, right? So, this is the distance measure in all the axes, and you square them and finally take the square root. This is basically the Euclidean distance. As I said, if you have 2 points, you just take a measuring tape, measure the distance between the 2 points. That's what you get. Uh, so there are two other, concepts of distance in which you can measure your distance. One is the Manhattan distance, which is basically just the modulus of the difference between the 2 points and summation over all the axes. So this is, this thing is, you have to square and take square root, square and sum, and then take square root. In this case, you don't square it. you just take the modulus of the distance between the 2 points. This is the Minkowski distance. This is also known as something as LP norm. So if you are familiar in linear algebra, it's called LP norm. But yeah, if you haven't don't have any linear algebra background, don't worry about it. It's just a name. So what you do is that it is similar to Euclidean distance, just in the place of this square, this two, you just take any other integer. Let's say p, right? So it could be like p could be 3, 4, 5, 6, anything, right? And then you just take the 1 by p times. So this is just another measure of uh, distance. There is nothing special about it. Depends on your problem to problem, like which measure of distance would give you the best estimate. But apart from that, I think yeah, I think this can also be treated as hyperparameters. You see, like this p parameter, this could be treated as hyperparameters. You can like fit your Cannon model on different, with different p's, and you will get with some p's you can get a better result, whereas for some p's you can get a not so good result. Okay, so okay, now these are the concepts of distance. Now, what about, let's say, you have some features which are more important than others, right? So let's say you have so in the previous example, if you say, gene 1 and 2, right? So if let's say your gene 1 has more importance in determining whether this mouse is obese or not, right? So what you will do is that you will obviously give more weightage to gene 1 and less weightage to gene 2, right? So you don't have to, like, earlier what we were doing is that we are giving equal weightage to um, all the features, but you can give higher weightage to some feature, whereas lower weightage to other features which are not as crucial as the others in determining the uh, obesity of the mouse or anything, right? So how do you weight your you know um distances, basically, right? So that was one way that which I was saying, that giving more weights to features. Now we'll see that instead of giving more weights to features, we can also give more weights to data points. Okay, so if you, let's say, you want, in this example, so you want to give more weights to the nearer points. Let's say you have fixed some value of k. So let's say you're using kn with k equals to 7, right? So basically these are all your points. Okay, and but you can choose to have all the points uh, in your while determining your new example, right? So you can choose all the points, but you can assign different weights to different points. So for example, for the nearer points you can assign higher weights, whereas for the further points you can assign lower weights, right? So in that way also you can do kn. In that case, you don't have to fix a particular value of k. You just have to fix your weight so that it gives more weights to the nearer points and lower weights to the further points. So this is, if you see this table, distance weighted kn. So this is how you decide your weight. So weight is inversely proportional to distance square. So distance, so if you see, like, if you have nearer distance, smaller distance, your weight will be higher. Okay, because the denominator is more, sorry, denominator is less, your weight is more, right? And then you calculate the this weighted distance to all the points. You sum it up and you see whether that will be in class 1 or class 2, or yeah, class A or B, whatever, right? So that is one way to do it. Another way could be, find this, fix this weighting functions. So these are fixed quotient, fixed y square, adaptive quotient, adaptive y square. So I'll just briefly explain, like, what it does, from a physical point of view. So you see, if you consider, look at this graph at the bottom. So this is your new example. This cross, this X marks the new example that you have to classify, whereas the dots are the examples which are present from earlier, right? So this is what your weighting function would look like if you are fixing it with the Gaussian function, right? So with the Gaussian function, if you see, this is exponential of minus This is dij. This is the distance between 2 points I and j divided by b whole square. So b is kind of the bandwidth. So I will tell what this physically means, what this bandwidth physically means. So dij is clear, right? It's the distance between the 2 points. So we just saw like how to calculate the distance, right? Now we'll use the distance to calculate the weighting function, right? So b is some basically fixed value. Okay, this is a constant. You can choose it on your own. So, but this is how this wij will look like. So, if you see, so from the cross, as you go further, your weighting function is decreasing. So, that's what I was trying to say. So, you're giving more weights to the nearer points, whereas you're giving lower weights to the further points, right? And this is how it is decreasing. So, this is how this exponential of minus this part looks like. This whole function looks like, right? Now, if you increase your B, so what is the physical significance of B? Is that if you increase your B, this distribution will become, broader. This is the basically the bandwidth, right? So this distribution will become broader. Whereas if you decrease B, this distribution will become sharper, right? So this is how it is, right? And then adaptive Gaussian is just, this will depend on the value of k that you choose in your knn algorithm, right? So this is the same, but just, for if you choose a particular k, then you can, like, it will depend on that. The bandwidth will depend on that particular parameter. Okay, so here the b is constant, whereas here the b can change, right, for different points and so. Well, okay, similarly for pi square, what happens is that if you look at this function, this is 1 minus distance by, again, bandwidth whole square, uh, total square, if dij is less than b. So here what happens, if you choose a bandwidth and, if your distance, if your points are within that bandwidth, it will have some weight. Whereas if that point is beyond that bandwidth, it will assign a weight of 0, right? So this is basically cutoff, right? Beyond which your weight is 0. Whereas if you are within this bandwidth, your weight is calculated like this. This will also have, give more weights to the nearer points and lower weights to the further points, right? Okay. So is that clear, or should I, like, draw some graphs and so on? Like, I can do that as well. But is it clear from what I said? Distance measure is not clear. So which part? Is it the Euclidean distance or the weighted distance, or all the three? Okay. Let me just quickly, open this. Okay. Let me just tell you how to, calculate this. So, so let's say again, you're classifying your mouse. This is the gene one value. This is the gene two value. Right? So let's say you have like 3 points, three mouse. So, let me, so these are the red points are in class A, and the black point is in class B. So 1 point is in class B, whereas 2 points are in class A. So now let me tell you the coordinates of the points. So basically this has coordinate, let's say gene 1 value is 5, gene 2 value is 4. This one has gene 1 value as 4, gene 2 value as 6, and whereas this point has gene 1 value as 2 and gene 2 value is, let's say 3. Okay. So this is how it looks. Okay. Now you have a new point. Okay. So this is your new point, right? So this has some coordinate value of, let's say, uh, you know, something between, let's say, 3 comma 5. Okay. Now, what is the distance between this point and this point? So this is just the Euclidean distance, right? So the Euclidean distance will be Just, x1 minus x2 whole square plus y1 minus y2 whole square. Yeah. So this is basically 3 minus 2 whole square plus 5 minus 3 whole square root. So I'm not normalizing it here, but you have to, normalize it as well, you know. But so first, basically, what is the idea is the first you normalize all your data and then you take the distance. So this will come out to be root over of 1 square plus 2 square, that is root 5. Right? So this is how the Euclidean distance looks like. Is that clear now? Okay. Okay. Now, similarly, you can calculate the distances to this point and this point, right? Okay. So quickly, if we see the distance between this point is root over of 4 minus 2 whole square plus uh, 6 minus 3 whole square. Yeah. So that is root over of 2 square plus 3 square. That is equal to root 13, right? And this one, this distance is root over of, uh, sorry, am I? Okay, so sorry. So this is the coordinate of 3 comma 5, right? Okay. So this is 4 minus 3 whole square, 6 minus 5 whole square. So yeah, this is the coordinate, this and this with what we're comparing. So 4 minus 3 whole square plus 6 minus 5 whole square, right? So this will be again 1 square plus 1 square, that is root 2, sorry. Right? Okay, I think this right now. Okay. Now this distance. This is 5 minus 3 whole square plus 5 minus 4 whole square. Right? So this is again root over of 2 square plus 1 square equals to root 5. Okay. So this distance and this distance are equal, both are root 5, whereas this distance is root 2. So it is even smaller. So this is the closest point, right? This is the closest to this cross. Okay. So when you're using weights, right? So what will happen is that you are giving higher weight to this point, whereas you are giving lower weights to the remaining 2 points, right? So when you are calculating the weighted distance, basically you just put the value of dij in the weighting function that I just showed you, and you get some weight for, let's say this is point 1, point 2, point 3, and the new point is, let's say, you know x, let's say I call it x. Okay. So now the weighted distance would be basically, Mhm. Yeah, it's okay. Like 4 minus 5 whole square and 5 minus 4 whole square is same, right? You're saying this is 4 minus 5 whole square, right? Is that what you're saying? Yeah, 5 minus 4 whole square is same as 4 minus 5 whole square. So since this is a square, you don't have to worry about, you're taking 5 minus 4 or 4 minus 5. It's the same thing, right? Okay. So yeah, this is basically minus 1 whole square, right? So minus 1 whole square is 1, 1 whole square is also 1, so you don't need to worry about it. Now, yeah, with the weighted, so what you will do is that, calculate the weights and you will do W of x1 into D of x1 plus W of x2 D of x2 plus W of x3 into D of x3. So basically W of x1 is the weight that you assign to this line. So that you can calculate from the formula, the weighting Gaussian or whatever you take it, by square, whichever weighting function you take, that you can calculate from there by putting in dx1. And dx1 we already calculated, that is root 2. Okay, this is root 2, and again this is root 5, and this is again root 5, right? So this is how you get the weighted distance, right? Is it fine now? Okay. Uh, Yeah, this session will be recorded. Yeah. Um, and it will be available in my YouTube. So simultaneously, as I said, I will be running a YouTube live session as well. So those who want to, to join to see the YouTube live, they can also join over YouTube. I'll just share the my channel link so that you can see the previous recorded sessions on that uh, in the channel as well. So just for reference, I'll just share it here in chat. Okay. Okay. So yeah, so this is the channel where you can find all the recorded lectures of the previous weeks, and I'll also record all the lectures in the for the upcoming weeks as well. So, and in the comments, I will like post the links for uh, this presentation, and notes, and whatever hands-on Python notebooks that I will use. I will post that as well. So if you can visit this channel, you can find all the things that are covered, right? So yeah, without going into those, let me quickly go through the hands-on exercise. So again, so this will be shared with you, and you can like play with it uh, to anything, right? So for the first part, I will be using, right? These are nothing new. If you don't know Python, it's okay. You can just uh, look at these notebooks that I will share. You can just play with it, and I will explain in detail what are each of the functions are doing. And there are excellent documentation of all these functions in Google. So, for example, PD. This is the pandas library that I'm using. Pandas, yeah, library that I'm using here. So this is when I'm importing this pandas library as PD, and then I am using this function that is in this library, CSV function. So if you just want to know what this function does, you just Google, pandas read CSV, right? So the first link that comes as a result, you just look at this. This is the documentation of this. Of this. These are all the parameters that you can pass to this function, right? The separator, if you have a comma separated file or a tab and so on. These are the headers that you can give here. Then you have column names. So you will get a detailed description of what all these parameters. So again, if you don't know Python, it's okay. I mean, you can just go through my notebook that I will share, and if your name, and they just you know do it like that. Okay. Okay. So all right. Now, yeah. So yeah. Yeah, so this is the read CSV function. As I said, the first parameter is the file path parameter. Okay. So this is where you give the path of the file and the name of the file that you want to pass, and this is what I have passed. So this is just reading, you know, so this is the data set which I have downloaded, and I will share this data set as well so that you can download and try it out. And this is the data set which I've downloaded. I'm just reading this data set, right? And this diabetes data.head. So I'm just printing the head of this file. So by head, I mean, the first five columns. Again, you can just, you know, type pandas head. Okay. This will give you a description of what this function does, right? And what are the parameters it takes. Okay. Head, let's say n equals to 5. By default, n is actually 5, so it must be mentioned somewhere. Yeah, this is basically returns the first n rows. It says that it returns the first n rows. And if you are not passing this parameter n equals to 5, it will by default take the value 5 and will print the first 5 rows of your data set, right? So let's see if it does that. Okay. Now you see, okay, this is printing the first 5 rows of my data set. If I do, n equals to 10, it will just print the first 10 data set, the rows of my data set. Okay, very simple, right? No, no knowledge of Python is required. Yeah, I will share everything. Don't worry about it. Right. So, now let's see what the data set contains and what is the problem that we have to do. So this data set contains, datas of these are the parameters: pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, age, and so on. Right. So without going into detail, like, so for example, these are, you can understand, like, these are data for different persons, right? You can understand that. For example, for this person, 0th person, the glucose level is 148, and so on, right? And for this person, age is 50, and so on again. Now, what is the thing that you have to predict? The outcome. The outcome is, whether this person has diabetes or not. So if it's one, then this person has diabetes. If it's zero, then this person does not have diabetes. Now you have to, make a KNN algorithm so that if you get a new person, you have to predict whether that person has diabetes or not. That is your main aim, right? So the new person that will come, he or she will have some, these similar values. Let's say his or her glucose level is 90, blood pressure is something, skin thickness, and so on, right? And you have to predict whether this person will have diabetes or not. That is your problem statement. Is that clear up till now? This is very basic, right? Now, again, this describe function, as the name suggests, this is basically describing the data set. So this will just, calculate what is the mean, standard deviation, minimum, maximum, and so on. All these statistics that you can do. So these are part of pre-processing, right? So, all these machine learning algorithms have some steps that you have to go through, to make your model. And these steps, are more or less similar in no matter what algorithm you use. So first step is, read the data. Second step would be pre-processing. I will tell you, like, what does pre-processing includes. Third step would be, building the model, and fourth step would be interpreting the results. That's it. Okay. So these are the four simple steps that you have to do, and I will just explain what each steps contain. So pre-processing is basically, before you build the model, you just have to need to have a look at the data, whether the data looks okay or not. If there are a lot of missing values in the data, you have to impute those missing values, like I was explaining in the last example, probably in linear regression. Okay, so I was doing some hands-on with some problem in linear regression, and I just told you, like, how to do missing imputation using forward fill. Okay, so there are a lot of other ways to do missing imputation, and yeah, but that is part of pre-processing, right? Okay. So here again, we are just, making a copy of the data. This line is just okay. So, yeah, as I was saying that, here, just making a copy of the data, and, just doing some, this is where the missing imputation is being taken place. Okay. Using the copy of the data, I'm just imputing wherever I have zeros, I'm replacing it with NaN. So NaN stands for not a number. Okay. So this will just, take the zeros in which in these columns, glucose column, blood pressure, skin thickness, because you see, glucose can be zero for a person, right? Similarly, blood pressure can't be zero for this person. So this is what you get from this, by this checking the statistics of the data. So here you see, for this glucose column, the minimum is zero, but minimum can't be zero, right? For a glucose level for a person, right? Unless that person is dead or something, you know. So, that person has to have a certain level of glucose, and so on. So basically, by looking at the data, you understand, okay, whoever is taking that data, whoever is doing the survey and everything, he's basically, whenever he don't have data for that particular column, he is just putting it to be zero, right? So these things happen. So that's why pre-processing is, very important in practical life, right? So these things happen, and you just have to see, and during the pre-processing, and you just have to replace them with NaN, right? And now you're just checking how many are missing in each of the columns, right? So this step is just checking how many are null. So these are the for skin thickness there are 227 nulls and so on other values. So this is just to get an understanding of your data, right? Now you want to see how many of your so this step what it does, it is checking the outcome, right? Outcome and value counts just counts the uh, number of values in which outcome is 1 or 0, right? So if you see from this bar graph, so you have around 500 uh, people who do not have diabetes who have zero values in the outcome, whereas you have some 268 people who have diabetes in your data set. So your total data set contains of, let's say 768 per people, and out of which 500 has diabetes and 268 has do not have, sorry, 268 has diabetes, 500 do not have diabetes. Right? So why do we need to look at this? So let's say, your data set contains, 500 people, sorry, 768 people, and out of which instead of 268, if you have only, let's say, five people who have diabetes, then you can see, okay, my data is biased actually towards the non-diabetic people. You have very few data points who are with diabetes people, right? So in that case, what you can do, your model will not give a very good prediction because your model will not learn the people who has diabetes. So that is why you need to look at a balanced data set, So this is why we are looking at this parameter, right? Does that make sense? Okay. Okay. Now, okay. So this is the part uh, which I will, okay, repeat the bias part. So by bias, I don't mean the bias and variance. By bias, I just mean that your data set is inclined towards a certain set of people. So your data set has more, let's say your data set contains, as I said, five people only with diabetes, whereas remaining all are non-diabetic, right? So then your data set will only learn the non-diabetic people, and it will not be able to learn the your model basically. Model will not be able to learn the diabetic people. Your model will not know which are the factors which can cause diabetes, like high glucose, whether high glucose can cause diabetes or not, because you have so very few data, very few people with diabetes in your data set. So that's why your data set cannot learn it, right? So that's what I meant by bias, but don't confuse it with bias and variance. Right. So diabetes data correlation. Okay. So this is something again which was explained in the professor's lecture. But if you if you have not attended, not a big deal. So I'll just go to my notebook and I'll just give you the formula of what correlation means. Okay. So okay. So there is a space here. Okay. So there is something called Pearson correlation coefficient. Okay. So when you want to, calculate the correlation between two variables, x and y, what you do, your correlation would be uh, this thing, xi minus x bar times yi minus y bar divided by xi minus x bar whole square root and summation of the yi minus y bar whole square. So, so the denominator is basically the variance of y, and this is the variance, sorry, variance of x times the variance of y. Whereas in the numerator, you have the correlation between x and y. Now, what does this physically mean? Like the correlation between x and y. So it means that how well your two variables, the x and y variables, are correlated. And you know what is mean by correlated? So let's say you know you are plotting something. Let's say you have data about number of hours a particular student is studying, and you have the test score of that particular student, right? Of let's say you have 100 students, you plot the test score versus the number of hours that person is studying. Now you can, from your data, you can see, okay, as the number of hours the student is studying increases, the test score of that student is also increasing. So the test score and the number of hours the student is studying is linearly correlated, or positively correlated, you can say. That just means that when one variable is increasing, another variable is increasing. Or it could be vice versa as well. One variable is decreasing, another variable is decreasing. Whereas if another one variable increases, whereas other variable decreases, that means it is negatively correlated, right? So with change in one variable, you have to look at the change in other variable. So this x1 minus x bar is the change in the x variable. Yi minus y bar is the change in y variable. So if you see, if this change increases and y decreases, so then you'll get a negative value, right? So it will be negatively correlated. Whereas both increases or both decreases together, then it is positively correlated, right? Is that clear? So I will go into the detail as well when I in this. Uh, Notebook. So if you can see again, so these are the correlations, right? So this means that this column, this value represents how pregnancies are correlated with pregnancies. So obviously, the same variable if you are taking, it is the correlation will be one, right? It will if you increase pregnancies, pregnancies will increase, right? With if you are correlating with the same variable. Similarly, glucose with glucose is one. So if again, because there's the same variable, it will be correlation will be one. Whereas this value represents the correlation of glucose with blood pressure. So that means that if you increase glucose by some percent, the blood pressure will increase by 0.15 times of that increase, right? So this just means that. So how much increase in glucose would cause, 0.15 increase in blood pressure, and so on. So that is what this number basically means, right? Okay. And similarly, if you can see like negative correlation here, right? So if you increase, let's say, pregnancies, you'll this diabetes pedigree function will decrease. So that's what negative correlation means. And by how much it will decrease? It will decrease by this amount, 0.03. Okay. So this is what it means. So again, I have a better way to represent this correlation. So this is something called a heat map. Again, SNS.heat map. If you just Google it, it will give you the how to calculate this. And this just gives you the values of different parameters. For example, again you can read this as you are reading the previous table. So in this also has a beautiful colorful representation. So this sometimes looks good. So for example, how is glucose related to age? So if you increase the age, your glucose level will also increase. So that's why you see a higher glucose level in older persons and so on, right? So this is basically a correlation matrix represented by a heat map, right? So this is how you read it, right? So what we'll be seeing is that this last column. So this is the outcome column, right? And in this columns you have different features by which you'll be predicting outcome. So if you see this blood pressure correlation with outcome. So this number will give you an idea that how much uh, what is the significance of this blood pressure, this variable, in predicting your outcome. So this is what it means. So higher the correlation value with the outcome, higher is the significance of that variable. So that means this variable is more important. So if you see glucose has a correlation of 0.49, whereas blood pressure has a correlation of 0.17. So that means glucose has a greater power in predicting your outcome than blood pressure because it has more correlation with the outcome. So we'll come to this again later, when in the next slide when I'll be explaining feature selection. So I think, professor has also explained this. And, if you have gone through our lectures, you can see, this is one of the methods by which you can eliminate some features. So you can eliminate the features which has lower correlation with the uh, target variable or outcome, and you can, choose the features which has highest correlation with outcome and so on, right? So again, this is the pre-processing step. Is there any questions? Okay. So did you understand the normal correlation? This okay. Yeah, so it is nothing. Just I'm just plotting this numbers over here. So these are the same numbers. If you see, pregnancy's correlation with pregnancy is one, so that I'm plotting here. Glucose correlation with pregnancy is 0.129. That is basically rounded off to two digits, 0.13, and so on. I'm just plotting this numbers here. So this is just a nothing special. This is just a correlation matrix in a color represented in a colorful way. So that's it. So the color represents this. If you look at this color bar on the right, so if you are on the redder side, so that means it has lower correlation. If you're on the greener side, that means you have higher correlation, right? So you will try to look for more green parameters, right? So greener is better, redder is bad. Okay, so that's it. That's what the color means. Otherwise, I'm just plotting the correlation values from the previous thing. So this is just a representation thing. This is just to make it more aesthetic. Nothing special about it. Is that fine? Okay. So now we'll go into model building. Okay. So as I said, so this step, this step is basically, normalizing the all the features. As I said, this is a prerequisite to KNN algorithm. So first we normalize, and then we calculate the distance, and then we fix the value of k, and then using those using by calculating the distance, we choose the k nearest neighbor, and finally we classify them whether they have diabetes or not. So that is the idea, right? So here I'm normalizing in this step. So if you see, this is a standard scalar function which basically normalizes it. Again, you can Google it and look more into it. I'll not go into the detail. But again, after normalization, these are the values that you get. Okay, you can look at the values, and this is the y parameter that I'm setting as outcome. So this is my y variable. So x variable and y variable is something which is our target variable. And again, as usual, we are this is just splitting our data into training and test set. So these are all the same steps that we have done earlier, right, in our previous week. So those who have not uh, not seen the previous week lectures, please go back and watch it. You will get better idea. But again, so this is just splitting into training and testing set, and then again, this is where we are building our KNN algorithm, right? So here, what I'm doing is for I in range 1 to 15, right? So I'm building basically 15 KNN models with K values 1 to 15, right? So I'm not building only one model, because later we'll compare which is the best model. So as I said, how will you choose which K will give you the best result? So that we'll see, right? So we are just fitting it for this is the fitting the training set with all the K values, and then we are just checking the test scores and training set scores and test set scores. So this is just the accuracy, how many of the uh, data points we are accurately predicting, right? So this is what it basically means, right? So again, so this model is trained. We are just calculating the training data scores, test data scores, and again. So here, what we are doing is just we are printing which is the maximum score that we are getting for our training set. So as maximum score that we are getting is 100% accuracy for k equals to 1, right? But if you have seen the previous lectures, you would know that our aim is not to maximize our training scores, because training scores is what the data is being trained on. We want to see how the model performs on some data which it has not seen previously, right? So that's why test score is the parameter that we should be looking at, right? So if you see, now we are calculating the test score, and we're seeing for which K we are getting the maximum test score. So we are getting a maximum test score of 77% for K equals to 11, right? Right? So this is what we should be looking at. And now we just want to plot, plot the values, right? So we just want to plot. So this is basically for, starting from k equals to 1 to 12, 1 to 15. right? So this starts with k equals to 0. So this should be actually k equals to 1. Okay. I think this has started one value previously from 0. But anyway, so this is for k equals to 1. So for k equals to 1, as I said, you have 100% accuracy. This is 1. And you have like some test. This is the orange line is the test score accuracy, but your test score accuracy is very low. So as I said earlier, if you have lower values of k, you should think about overfitting. And by overfitting, the first thing that should come to your mind is variance. So if you remember, in the first week's lecture and even the second week's lecture, what did I say about variance? For variance, you will have lower training error, whereas you will have high test error. So if you see, training error is basically zero because it is 100% accurate, whereas your test error is very high, right? So this is what. So for lower k values, you are getting a higher variance. So how to reduce higher variance? You will take more features. In this case, you will increase the value of k. So if you go further and further, if you see, for this value of k, your train score and test score are like, very close to each other, and, test score is basically maximized. So you choose this value of k, this value or this value, whichever. Both performs pretty well. Okay. So this is what this graph talks about, and this is how you select the value of k, right? Is it fine? Now, in this step, you just check your test score for this 11. Here I am taking the k value to be 11. You can check the test score. The KNN score for k equals to 11 is 76. You can play with it. You can just check what is the test score for k equals to 12. It will give you the test score. It has a lower test score, 75%. Previously, for 11, we had 76%. Okay, 77%, actually, right? So this is how it is. And these are some more things that you can do. This is the confusion matrix that you can plot. So again, you can look into the first week's lecture, where I taught what the confusion matrix looks like. And yeah, so you can look into it. This is the predicted 0, predicted 1, true 0, true 1. From here, you can, calculate the precision, recall, and F1 score, and so on. So many things. Okay. Again, this is again the confusion matrix again with the color plot. This just again looks aesthetic, looks good with colors. Yellow colors means lower values, blue color means higher values, and so on, right? So if you are to calculate precision, you just take this divided by this plus this, and so on. Recall this divided by this plus this, and so on, right? I'll not do it, but you can go into the first lecture and try it yourself, right? So it will give an idea, right, how well this model performs. So this is it for Canon. Any questions? Time to answer your question that if we so what a question is that if we increase the value of k to further values, till now we have checked only for 15. We can increase the k to further values, let's say 16, 17, 18, and it might happen that the test error could increase, right? That could happen, right? But you know a good way to see is try it out. Okay. uh, to give you the answer in short. Okay. So from here you can like play with the code, and in case of 15, you can just replace it with some value 100, or so on, right? So you can just try it out and see what is happening. But I would say that after a certain value, the test error will increase, or test accuracy will decrease further. Why? Because as I said, if you are, increasing more and more values of k, you're including more and more data points, so basically what you're doing is that you're doing the opposite of variance. So basically on the first side of the graph, for lower k values, you have high variance, whereas for the higher k values, you're doing the opposite. So you're basically underfitting your model. And that will be the case of high bias. And what happens in case of high bias? You have high test error, you have high training error as well. You have both the errors high. So basically, both the accuracies will go down, right? So basically, that's because you are underfitting your model, and that will give you high bias in your model. Does that, answer your question? Is that what you're asking? Hmm. Mm-hmm. Hmm. Right. Uh, yeah. So as I said, you can like go up to a particular value. After that, as bias increases, you can like see a trend. You can calculate it for 20 and 20, 30, 40 for further k values. You can see a trend that both the errors are increasing. That is, accuracy is decreasing. So then you will see, okay, your model has high bias. So then you don't need to check further, right? So that will is that what you're asking, or am I? Yeah, yeah, yeah. True, true. It is. You can check only up to a further value. Right? You cannot check for k goes to infinity. You cannot go till infinity, right? You can check only till a finite value, and after that, you just have to see. Okay, now after this value, training error and testing error both are decreasing. So both are increasing. Testing accuracy, training accuracy, both are decreasing. So your model is having high bias. You just leave it there, and you choose the best k value and move on. Right? That's what you do. So what type of project is asking what type of distance metric works best? So yeah. So as I was explaining, these are the different type of distance metrics that you can use: Manhattan distance, Euclidean distance, Minkowski distance, and then you can like use weighted distance as well, right? So where you can weight the distance. Now what kind of distance metric works best, it is very hard to say without knowing the problem and doing the pre-processing. So again, this is something which you can do in your cross validation as well. Okay, again, this is the hyperparameter tuning again that comes in. Okay, so what you can do, you can build your model on Euclidean distance, and you train your model on that, and you test your model using this. You check the error, what are the test errors, okay? And again you choose a different distance, let's say Minkowski distance, and again you check the test error on your cross validation set, and you see, okay, now you see that, okay, for using Minkowski distance I am getting a lower test error compared to using a Euclidean distance. Then you say, okay, now this is the distance that which I should use going forward for our model, right? So this is how you basically choose the distance. This highly depends on the data that you are using. We cannot say that this distance is better than that, or this is dependent on the structure of your data, right? Is that okay? Okay. So okay, coming to feature selection. Okay, so we are running a little bit late, so I'll try to you know uh, go faster, but feel free to stop me anytime. So, okay. So, why do we need to select features? Why can't we use all the features that we have in our hand, right? So, this is because we can have some irrelevant features which are not contributing to our model, you know. So, for example, you're trying to predict what is the test score, what is the, examination score of a particular student, and you have the data such as, whether that student can, let's say, play cricket or not. So okay, so that features won't help me, predicting the examination score. Okay, that is those two are independent things. Someone can play cricket as well as do good in exam and so on, right? So those features cannot contribute well in our model, right? So those are the irrelevant features. Redundant features again. So for example, I gave this example in the first week. So for example, if we have a you're predicting the housing price, and you have in your feature you have one as the size of the house, the length of the house, and then you have like the square feet of the house, which is basically length square, assuming that it's a square house. So you have length as well as length square in both the features in your model. So the one of the features is redundant, right? If you already have length, you don't need length square, right? It's already been taken care of. Limited training examples. Again, so you don't have, infinite training examples. You have some limited training examples, and you can only, taking more features than the number of examples that you have is kind of a, ill-conditioned problem, right? So again, if you don't know what is an ill-conditioned problem, that's okay. But the fact is that you cannot have infinite number of training examples, so you need to have some limited training examples, so you have need to have some limited features as well. Limited computational resources, more the features you include, more your computational power is required. So you don't have infinite computational power, so you want to minimize your features. So again, this is the graph, which is, if you increase your variables, so first your performance increases and then it decreases, right? So because you are including redundant features, irrelevant features, and so on, so that's why your performance will decrease. So we need to, select the features which are only relevant for our model, and that's why what we want to use. Okay. Now, there are two broad methods in which you can select your features. One is supervised and is unsupervised. So supervised is also called wrapper method. This is after you have built the model, then you select your features. Whereas unsupervised is something which you can do before even if you build your model. So in supervised, you can have like two methods. One is forward propagation and this backward propagation. So I think I explained briefly about these two methods in the first lecture when someone asked me a question on this. So forward propagation is something, so what happens is that let's say you have ten features, whereas you're predicting some a target variable y. So what you do is that you choose the first feature first, okay? And then you fit your model, okay? And then you check the accuracy, error, and everything, right? And then what you do is, okay, now you choose the second feature. So you use the first two features together, then again you train your model and check the accuracy and everything, right? So now you see, okay, by adding the second feature, is my model giving a better output? And if it's giving a better output, how much better? Is it too much better or is it a little bit better? If it's a little bit better, then we can ignore the second variable. We can go on to the third variable and so on. That we can do. That is moving forward until we have exhausted all the list of features. And backward propagation is basically the opposite. First, we build our model on all the 10 features that we have, and then we remove one feature, one by one feature. And we see that, okay, by removing this feature, whether my model performance is increasing or decreasing, and if it's decreasing by how much. Okay, if it's decreasing by a significant amount, then okay, we can, this is an important feature, we cannot remove it. We will try with separate other features, and we'll see which feature is more important, which is less important, and then we finally build the model with the best set of features that we have. Okay, is that fine? Okay. Moving to unsupervised learning. As I said, unsupervised learning is done before you build the model. So in the supervised learning, you have to build the model, but in unsupervised model learning, you don't have to build the model. As I said, these are some of the things that you can calculate. So for example, Pearson correlation. So this I extensively covered. This is the formula that I wrote, and again I have calculated the Pearson correlation in the in the this notebook. If you see, I'll go to it again. If you see, this is basically the correlation graph, right? So this means, as I said, I explained earlier, how is so this number 0.23, let's say, this number tells you how is glucose correlated with skin thickness. So if you see, okay, this is a very high correlation, then you can say that, okay, so let's choose one variable, okay. So this is, let's say, 0.65. So that means BMI is related to skin thickness. So these two variables are very highly correlated, BMI and skin thickness. So if these two variables are very highly correlated, you don't need to include both the variables in your data, right? You can do away with one of the variable. You can keep only one variable, right? You don't because your model will perform equally better with one of them in your feature set, right? Whereas the variables which are not very highly correlated, for example, BMI with pregnancies and so on, then in those cases, you need to keep both the variables, right? So that is the idea for Pearson correlation. And similarly for SNR ratio. So this is the formula for SNR ratio. Okay. This is the difference between the means of the two variables divided by the standard deviation between the two variables. So again, higher the SNR ratio is higher the power of that variable to predict your. So yeah, again I forgot to mention one thing. So in the Pearson correlation also, if I go again to the heat map, so here you need to see also that how good is this glucose variable in predicting your outcome. So glucose is very high correlation with your target variable. So this is a very important variable. You must include this variable. Whereas some variables which has lower correlation, for example, this 0.17 correlation, diabetes pedigree function, this variable might be excluded because it has lower correlation, right? So you need to also check the correlation of your variables with the target variable. In that way, you can determine which is a better variable, which is not so good variable, and you need to keep the best variables to in your model. And similarly, SNR ratio will check the SNR of glucose with the outcome. It will give you a different number, and again, higher the number, higher is the significance of that variable, and you should include variables with higher SNR and so on. So again, mu x is the mean of the variable, mu y is the mean of the outcome target variable, sigma x and sigma y are the standard deviations respectively, right? So yeah, Niryogi. Correlation. Right, right. If two variables, two features are very highly correlated, you can remove one of them because that would have redundant features. Yeah, Pritam. No, no. So I was saying, so there are two distinct things. Okay. So let me just go to it again. So there are two different things that I said. Okay. So this is the target variable. Outcome is your target variable. Okay. So one thing is you have to check is how two features are correlated with each other, right? So that means if let's say, as I said, BMI is correlated with skin thickness, that means both the variables, both BMI and skin thickness, can predict, have same predicting power. So you can remove one of them. But then you see, like you will see that if you want to see which one of them, let's say BMI and skin thickness, which one has higher predicting power in predicting the target variable, then you have to see the correlation of BMI with the target variable. So correlation of BMI with target value is 0.31, whereas correlation of skin thickness with outcome with your target value is 0.26. So then you see, okay, BMI can predict my target variable better than skin thickness. So you keep, okay, BMI I can keep and I can remove skin thickness. That way you can decide, right? Is that fine? Okay. So there are two things. One is the correlation within the features. One is the correlation with the uh, target variable, right? Okay. So moving on. Okay, PCA. So this stands for principal component analysis. So why do we need principal component analysis? So these are the reasons. First is dimensionality reduction. So you have like 100 dimension data, right? So you have to reduce it to lower dimension. Why do you need to reduce it? It can, help you visualize better. It can get rid of redundant dimensions, okay, and so on. Another is, you have to reduce your noise, right? So you can reduce the uh, yeah, as I said, irrelevant features and irrelevant dimensions you have to reduce, and that will reduce your noise. So even there are some signals even as coming from brain signals, ECGs to to even astrophysical signals, astronomical signals, and so on. Whenever you have signals, you will have some noise component to it, right? So this PCA is a very powerful tool to denoise the signal, right? And it has been used in many applications, right? And this visualization, as I said, lower dimensional data is easy to visualize. So you can like plot a two-dimensional graph easily on your two-dimensional paper or anything, but you cannot visualize 100 dimensional data, right? feature engineering. Again, you have to remove the redundant features. You have to remove the features which are not very significant in your prediction, and overfitting problem. Again, so as I said, if you are using more and more features, you are basically overfitting your data, right? You are whereas that will cause very high variance. To get rid of that high variance, you have to reduce the dimension of your data, and you can then get rid of variance problem. Again, data compression, this will also reduce the size of your data, and make the algorithm faster, and so on, reduce the computational cost, and so on. Okay, some of the terminologies that are associated with PCA. Yeah, so I will quickly go to my notebook, and let me see. Okay. I will explain some of the things. Okay. Sum of squared distances, variance, eigenvectors. Okay, so I will basically, explain what this each of the term means. Okay. Okay. So let's say this is your x1 and x2. These are, let's start with 3 points. Okay. This is your x1, x2. Now you want to reduce this 2 dimension to 1 dimension. You draw a line, and these are the perpendicular distances to the lines, all for all the 3 points. Let's say this is d1, d2, d3. So your sum of squared distances, or SSD, is d1 square plus d2 square plus d3 square. Now you look for the line which has the minimum SSD, right? Okay. Now this is SSD. Now what is variance? So you see, so variance is basically how far are these points from origin. So if you look at this figure, okay, so you see the variance is measured as this. So how far are these points from this? How far spread across are these points? Okay, so for example, so after you have drawn the best fit line, what you do is you project these points on this line. So this will be the projection of this will be the projection of this will be the projection of this. Now what you do is you rotate this line, and again I'm just plotting the same line with the same points. Okay, and now this is your 1D data, which has been reduced from 2D to 1D. So this is your representation in 1D, and your variance is how far across spread is the other points in this new dimension of data. So this is your variance. Okay, so basically, minimizing your square sum of square distances is equal to maximizing your variance, right? So you're basically trying to see which is the maximum variance that you can get from this line. So if you are minimizing this distance, you're basically maximizing this distance. Okay, right? These two are equivalent. Okay, and how they are equivalent. So I think you all know about Pythagoras theorem. So you see this is the hypotenuse, right? This is the height, this is the base. So if you are minimizing the this thing squared of some distances, then you have to maximize this thing, right? So lowering this, keeping this hypotenuse constant is basically increasing this thing. So this is the hypotenuse. This is the height. Perpendicular. Let's say this is the base. So hypotenuse square equals to perpendicular square plus base square. So if you are minimizing the perpendicular, right? So keeping this constant, if you are minimizing this has to increase. This will be maximized. So these two are equivalent criteria, right? So basically, what you're doing is minimizing SSD and maximizing variance. Okay. So what is the third terminology? Let's see. So third terminology is eigenvector. Okay. So eigenvector is, so if you see from here, right? So what we are doing actually, So if you are familiar with linear algebra, it is good. But if you are not, what we are doing is, we are taking a part of x1 dimension and a part of x2 dimension to create this new dimension. Okay. So let's say, uh, let's say in constructing this vector, you are going a little bit towards this side, let's say zero point 0.5 units towards x1 axis, and let's say zero point 0.8 units towards y1 axis. So 0.5 x1 plus 0.8 x2, that will be your new x axis. Okay. So your eigenvector would be basically 0.5, 0.8. So this is your new vector. Okay. This is how. Okay, sorry, I'm not sharing the screen. Yeah, extremely sorry. Okay. Yeah, so as I was saying, in constructing this new vector, you're going zero point 0.5 towards x1 direction, zero point 0.8 towards x2 direction, and so you're getting the new vector over here. So that's how you get the eigenvector. Your 0.5, 0.8 is your new eigenvector. Okay. Uh, yeah. So that is next terminology is yeah, eigenvalues, loading scores, eigenvalues. So yeah, um, these I will skip scree plots. Okay, so these I will explain, while I am doing this hands-on. So I have this hands-on exercise on PC as well. I'll just explain on the go. Okay, the remaining parameters. So again, we are importing the libraries. So here, what is happening is that this is a library of, faces of people. So I have 400 images of faces of people. So I have 40 people, and each people has 10 different faces. So in my input data, I have faces of 40 people. So one could be, looking on, so I have 10 faces for each person. Okay. So one face could be, of one person looking towards the front, one person looking towards the right, and so on, in all varieties. So I'm just loading the data, my test data and training data. And then if you want to see an image of the data, so this is one of the images, right? If you want to see another image, so you can just change here, and this is an image of another person. That's how it looks. Okay. If you want to see another one, you just change the image number. Let's say this one, you get another image. Okay, this is another person, another image, right? So how are images stored in your data set, right? So if you see, if I'm just printing an image, so this is one of the images, right? And I'm just printing that image. So this is basically stored as an array, right? So what does an array represent? This array represents the what are the RGB values of each of the pixels. So basically, this has divided the entire set into 64 pixels, and it is just telling me what are the RGB values of each of the pixels. So if someone has more grayscale here, then it will have some different value. If it's more darker here, it will have different value, and so on, right? So basically the point is that images are stored as arrays in Python, right? uh, so again, total images are 400 and total classes are 10, because I have 10 images of each person. And here I'm just looking at the shape of my data. This is how I am splitting the data into training and test sets. And here is where I'm reducing doing the PCA. So I am just reducing the data into 100 basically components. So I'm reducing my this big data into only 100 samples, or 100 dimensions, right? You can choose 10 dimensions as well. Let's to go with 10 dimensions. So here what will happen is that we'll get 10 dimensions, we'll get eigenvalues for 10 dimensions, and finally we'll see like how it is, right? So firstly, we are just training my data and testing my data over here. So let's go ahead. And here what I am doing is that I'm just printing all the eigen faces, right? So in this case, what you will get is the eigenvalues of your data, right? So here it is, right? So these are the eigenvalues. So you see, like by using these eigenvalues or eigenvectors corresponding to these eigenvalues, you can construct any image of which is given in your test data. So this is the idea, right, of these eigenvectors and eigenvalues, right? So eigenvalues will basically tell you like which eigenvector, which feature is most important, right? So you can choose the top five most important features and then use that to go further and build your model and so on, right? So that will tell you. So this is the importance of eigenvalues. So higher the eigenvalue, more important is the feature. So again, eigenvalues are basically these variances basically which I just explained. So actually these are the square I think variance divided by number of terms. But again, the point is that these eigenvalues are directly proportional to variance. So higher the variance of higher is your eigenvalue, right? So again, now I'm just printing the shape, and here what I'm doing, okay, street plot. So here you see, okay, so this is the eigenvalue for your first eigenvector. Okay, there are 10 dimensions. So this is the eigenvalue for your first dimension, eigenvalue for second dimension, and so on. So if you see, the first dimension is is contributing actually 25% to your model. Second eigenvector is contributing 15% to your model. Third one contributing, you know, let's say some 8% and so on. So if you see towards the last, these eigenvectors are not contributing much to your model. So what you can do, okay, reduce, you can, remove these eigenvectors, and you can only build your model on the first, let's say, four or five, eigenvectors, and you can proceed forward. This will give you a very good accuracy, and this will also reduce your dimensions of your data, and help in feature selection, selecting the best features, and so on, right? Is there any question so far? Okay, Mainak is saying, yeah, please. Difference between what? Sorry, come again. Right, right. So eigenvectors are this. So here I am plotting the eigenvectors actually. Eigenvectors would be the features. Basically, they will be used as features in further processing. And corresponding to each eigenvector, you will have an eigenvalue, and that eigenvalue would be directly proportional to the variance of data in that dimension, and that will give you an idea that how important is that eigenvector in predicting your model. So eigenvalues will give you importance. Eigenvector are actually the features that are being used to predicting your data. Uh-huh. Right, right, right. Yeah, so eigenvectors are this series of, so as told you earlier, like you can these pictures are basically saved as arrays in this case, right? So these eigenvector, this is one first eigenvector, let's say, this will be a array, right? So now what you do is, and again so on, this all this will be arrays. Now if you say that okay, the eigenvalue corresponding to the this eigenvector is maximum, that means that this array will be most important in predicting your new feature, new image that will give, right? So you can like ignore these last four features, last four faces, and you can just use the first, let's say, six faces to, and use a combination of these first six faces. Like I can use 10 times this face, which will brighten the face or so on, and five times this face and four times this face and so on. Use a combination of these faces, linear combination of these faces, to predict a new face that your model will encounter, right? And what I mean by a combination of faces, these faces are basically arrays. So five times an array plus six times an array is just giving a new array, and that new array would be your prediction for your face, for a new face that you will get. Is that clear? Right, right, right. Exactly. Okay. So Mainak has asked PCA can reduce the dimension of the model that has 30 features and I get 5 to 6 principal components. I can do that, right? Yes, you can do that. Is there a thumb rule that how many principal components we can get at max based on the number of features? Yeah. So if you have, so this is a dimensionality reduction method, right? So if your initial data has 30 dimensions, right? So you cannot get more than 30 dimensions. You have to uh, reduce it, right? So your maximum number of features will be 30, right? Is that does that make sense? You can get any number less than 30, but your maximum would be 30. Okay. So linear discriminant analysis. This is another method to reduce the dimension of your data. So here, okay. So in PCA, what we used to do is that we did not have any class. Okay. So we didn't say that okay, this is class A, this is class B, and so on. Right. Now we have added a tagging to the data. So the green variables are the uh, variables which are of class A. Red points are the points which belong to class B. Now what we want to do is we want to separate these two class by using some method so that we can say okay, this part is class B, this part is class A, and so on. So what we want to do is that separate the mean of the class as well as simultaneously reducing the variance within the class. Okay, so that is an important one. We want to reduce the variance within the class, not the total variance, right? So let's say you have this data. Okay, so this is the initial data that you have. If I am showing the pointer right in the 2 dimension, okay, this is the initial data. So what will happen if you just use PCA? If you use PCA, you will get this left side graph that you have. So if you can draw a line like this, which will like minimize the sum of squared distance, maximize variance, you'll get this kind of graph. But if you get a lower dimension, you have reduced the dimension successfully. Okay, I mean, you're doing good. You have reduced the dimension successfully, no doubt about that. But is this model able to predict? Is this model able to separate the two classes? The answer is no, because you have some mixture of classes in between, right? So if you see, this is a green point in between the red point. So it is not able to separate the two classes, right? So although it has reducing the dimensions well, PC is reducing the dimensions well, but it is not doing a great job in separating the classes. So what we will do in separating the classes is we'll check that to separate the means between the two classes. So the green mu is the mean of the first class, red mu is the mean of the second class, and the variance is s square in green, and this is the s square in red. Okay, so what want to do is we want to maximize the distance between the two classes, the means of the two classes. So we want to take the green line and the red line farther apart, and we want to minimize the variation. So we want the green points to be clustered together, red points to be clustered together, so that we can clearly separate between the two classes. So that was the difference between PCA and LDA, right? So yeah, so this is, if you are given this data, so after you have applied, so if you are, let's say there is a case, if you are only maximizing the distance between the means, so this is what you obtain. But if you are maximizing the means and simultaneously decreasing the variance between the two classes, this is how your data should look like. This is the line that you actually should choose, and this is the line on which you should project your data points. So if you project the red points on this line, you will get this. If you project the green points on this line, you get this. So now you can see that you can clearly separate the two classes, right? So that is the difference between, PCA and LDA. Is that clear? Okay. So yes. Okay. So this is the last slide. Okay. So this is, recommender systems. Uh, again, so there are two types of recommended system. So what is recommended system basically? So if you see on this right side, you have names of four books. Okay, these are books, literature books, and these are four people who have rated these books out of five. So Alex has rated this book Northanger Abbey as five. Alex has rated Wuthering Heights as four, and so on, and other people. Now you see, okay, this Taylor, he has not rated he or she has not created this book, Bondswoman's Narrative. So here is null. And again, Ainsley has not created Northanger Abbey. So here you have null again. So now what you want to do is that, you want to see like what will these guys, if these guys had rated this, how will they rate this, right? So you want to know. So again, there are two methods. One is content based, one is another is collaborative filtering. So I'll just mention content based, but I will not go into the detail. So content based is that, so when you go into the Amazon site, okay, so now you look for some, clothes or something, and you see next time you go to the Amazon site, it will recommend you similar clothes and similar items, right, which you have previously searched. So that is basically a content based, how the content based algorithm works. So it will look into, how, how you have previously searched your, it will look into your history, what are your previous searches, and then it will look into, and it will recommend you new items based on your previous search, right? So it will recommend you similar items. And how do you, uh, measure similarity? That I will come to in a moment, right? So again, that is the way how content based learning works, recommended system works. And second one is collaborative filtering. So collaborative filtering is, again, so this is something like it will look into not your history, okay, it will not look at what you have looked at in the past, but what will it will do is it will look into what other users have, rated item, right? So and then it will see what is the similarity between that user and you, and then it will calculate what will be the rating of that particular item, right? So again, so this is how you calculate the similarity, and so I'll just quickly show in principle how you do it, right? So again, I'll just explain the formula once. So this is the similarity between user A and user B. So this is summation over, or summation over rating of A for a item I minus the average of user A rating times rating of user B for an item I minus average of user B rating. And this is the variance terms. Okay. And again, similarly, for item-based filtering, what you will look is that similarity between two items. So here you are looking at similarity between two users, and then you are calculating the prediction. And on the other hand, here you are looking at the similarity between two items. Okay, so this one and this one. So what is the similarity between these two books? And based on the similarity, you will predict what will be the rating for this Northern Abbey by Ainsley. Okay, so based on the similarity, you select your score. So let's say you test the similarity between these two users, and you get some value, and now you want to predict what will be the value for this, how rating for this, and you check the average rating for this user for Ainsley, plus you just do the, this is again the rating for ith item by user A minus the average of user A rating times the similarity of with other users divided by the summation of similarity. So again, I think it will be more clear if I just do one calculation for one of the items, right? So let me just go to my whiteboard. Okay. So what I will do is that I will just do the uh, make the table first. So this is the okay, wait, visible. Okay. Okay. So these are the books NWOB. I'm just writing the initials of the books. These are the people. Alex, I think the first name, Lauren, Taylor, and Ainsley. Okay. So these are the four people. Now, how they have rated the four books, we'll just look into that. So this is rating 5, 4, 3, 4, 1, 2, 4, 5, 1, 2, 3, null, null, 4, 3, 1. Okay. Now what we'll do is we'll write the average. So average of all the ratings by Alex is 4. Okay. So if you just take the sum and divide by 4, that will come out to be 4. Average rating for Lauren is 3, Taylor is 2, Ainsley is 8 by 3. So this is basically 4 plus 3 plus 1, 8 by 3. Okay. This is the average. So now we will also look at the average of uh, you know of this item. Okay, this will help you in calculate of the n of this book. So this is basically average is 7 by 3. For this book, W book is 3. For this, O is 13 by 4. B is 10 by 3. Okay, these are the averages that I have just written. Okay, now what I will do is I will calculate the similarity between two users. So let's say I want to predict this value, this x. Okay. So now what I need to do is I need to calculate the similarity between Taylor and all the other users. So let's say I calculate the similarity between Taylor and Alex. So T and AX. So what I will do is, uh, I will check this value 1, uh, and this is the first value 1 minus the average. So if we look at the formula, so let me just, bring this side by side. Okay. Uh, okay. So this is the similarity formula. Let me just magnify it and let's move it. Okay. Okay. So this is the formula, right? And okay. Think- okay. I'm not able to do it, but again. So let me see. So I'll tell you. Okay. So 1 minus the average of Taylor's rating. So 1 minus 2. 2 is the average times, uh, you know, the other rating 5 minus the average of Alex, that is 4. Okay. And we have a summation. So we will sum over all the books. So this is only for, the first book. Then we'll go into W book. So plus 2 minus, again, 2 minus average 2 times 4 minus average 4. Again, this will be 0, but, and then we go on to the third book. So 3 minus 2 times 3 minus 4, and this is null, so we'll leave it out. Okay, so this is the the numerator, if you see from the similarity formula, and in the numerator, and in the denominator we'll just have the variance. So variance is 1 minus 2 whole square plus 2 minus 2 whole square plus 3 minus 2 whole square times the variance of Alex. So this is the variance of, Taylor. The other one is the variance of Alex. So it is 5 minus 4 whole square plus 4 minus 4 whole square plus 3 minus 4 whole square plus 4 minus 4 whole square. Right? So this is how you calculate the variance. This will come out to be basically, this will actually come out to be a very simple number, minus 1. Right? So similarly, uh, is the calculation okay? Like, uh, I did it in a hurry, so but if you have any questions on the calculation, so this is just using the formula that I have given there in the slide. Is the calculation okay? Okay. So if not, you can like go back and look at it. But similarly, you can calculate the similarity between Taylor and Lauren, similarity between Taylor and, okay, Taylor and Ainsley and so on, right? And now we want to calculate the rating of Taylor for this B book, okay? That will be basically the average rating of Taylor, that is 2 plus, so here is the average rating 2 plus, you know, similarity of Taylor with Alex times, whatever Alex's rating was for this book minus the average rating for Alex, that is 4 minus 4, okay? 4 minus 4 plus similarity of Taylor with Lauren times, you know, uh, Lauren rated this book as 5. So 5 minus the average rating of Lauren, that is 5 minus 3, plus similarity of Taylor with Ainsley times, Ainsley's rating is 1. Okay, this is 1 minus uh, average rating of Ainsley, 8 by 3. Okay, so if you calculate this whole thing, you'll get the answer. So yeah, you please, I think I have shown you how to calculate similarity, and you can calculate similarly the similarities for these two things. Okay, these Taylor with Lauren, Taylor with Ainsley, and finally calculate the uh, rating of Taylor for this book B, right? Yeah, so Monica is saying explain it once again. So which part is there any part that I should explain? Yeah, is there any part that I should explain it again? Like which part did you find it difficult to understand? Yeah, as I said, just use the formula, okay, and let me just. mm, yeah, I'm just using this formula. If you see, okay, yeah, I think this is. Yeah. So I'm just using this formula calculating the similarity, right? Okay, similarity of T with A. So I'm just using this formula. Now it is side by side. So if you see, we are summing over all the items. I stands for all the items. So here your items are the books. Okay. So let's say we'll go one book one by one book. Okay. Let's say I start with the N book. Okay, the not finger. Okay. So what I'll do is that, so these are between two users, user A and B. So in our case, user A is Taylor, user B is Alex. So what I'll do is that first rating of Alex for this book I and N book, this is 1 minus the average rating of Taylor. So that is 1 minus 2, right? So this is the first term, right? And now for the second term in the product, we'll see what is the rating of Alex for this N book. That is 5 minus average rating of Alex. This is the average. The bar stands for average. So 5 minus 4, right? Then summation over all I. Next we go to the next book, right? The W. So here, if you see, the rating of Taylor is 2. So this term is 2 minus average rating of Taylor. That is also 2, right? So similarly, for the next user, for Alex, rating is 4 minus average rating of Alex is 4, right? 4 minus 4, 2 into 2 minus 2 into 4, 4 minus 4. And then again, we go to the next book, that is O. So here, the rating of user A, that is Taylor, is 3 minus average rating of Taylor 2 times rating of Alex is 3 minus average rating of Alex is 4. So 3 minus 4. 3 minus 2 times 3 minus 4 divided by again the variance of this thing, again the same thing, right? So this is how you calculate the similarity. If you just go through the calculator and calculate this, it will come out to be -1, right? And then using this similarity, similarly you can calculate similarity of Taylor with Lauren, Taylor with Ainsley, and so on. And using this similarity, you can calculate the uh, rating of Taylor for this book B, right? Is that clear now? Okay. Okay. So yeah, this is how you calculate the similarity for user based, and similarly for item based. Okay. Uh, Item based, what will happen is that you calculate the similarity. So here, what you're doing is calculating the similarity between two users, right? And in item based, you will calculate the similarity between two items, right? So basically, you will calculate the similarity. So here we calculate it between Taylor and Alex, Taylor and Lauren, Taylor and Ainsley. There we will calculate similarity between this book, Northanger Abbey with Wuthering Heights, Northanger Abbey with Oromco, Northanger Abbey with Bondsman Narrative, and so on, right? So that way you'll calculate similarity, and then again you will calculate the average for this book, average for this book, and from again like that you'll calculate the missing values for that. Again, I'm not doing this calculation. This is something that I think it's a good calculation for you to do, right? And I think yeah. So that is something you should do, and it will like it's a good exercise, right? So is there any questions so far? Uh, like every week, I'll just end with a set of questions that you should think about and try at home. You know. So if you don't have any questions, so these are the questions that you can think about. So how can you perform regression using KNN algorithm? So I just discussed, classification using KNN. You can also do regression using KNN. So how can you do that? Uh, what is the problem if we choose an even value of k, right? So we have looked at, k in our hands-on exercise. We have looked at k values from 1 to 15, right? But there is a problem, if you choose an even value of k. And what is the problem that you might encounter that you have to think about? And what are the differences between PC and LDA? So I discussed some of the differences, but you should think about, what are the other differences? Why should we do PCA and LDA? And again, what are the limitations of PCA and LDA? What are the other dimensionality reduction techniques, right? So there are a lot of denoising and dimensional reduction techniques that are used, and each one has their own uh, advantages and limitations. So you should think about those. Maybe research a bit, Google a bit, and uh, you know so yeah, so the last part I did the calculation to calculate the similarities and calculate the rating. I think you should write a Python code to calculate the similarities and calculate rating for recommended systems. So basically what I did was that in the similarity calculation, this is nothing but the Pearson correlation coefficient, right? So if you see this formula, this is nothing but the Pearson correlation coefficient, right? So basically, we already know how to do correlation, right? We calculate the correlation matrix and everything, right? In our hands-on exercise with Python already. So maybe you can try with input this data set in that code, modify that code a bit, input this data set, and calculate the correlation between two users, and that way you can get the similarity between two users, and using that similarity you can calculate the uh, ratings that can happen. So these are the questions that you can like try at home and think about. And yeah, is there any question? So yeah, so everything, notes, links, and uh, PPTs and notebooks would be available on YouTube. And in the YouTube comment, I will tell you about the link. Okay. So everything will be available on YouTube, recorded and everything. So yeah, have a look at that. Any other question? If not, we can end the call, right? Okay. So uh, see you next week. Thank you all for coming. Yeah. Uh, okay. V is saying, can you please give some ideas about ML course projects? Uh, and there are a lot of projects. What kind of projects are you looking for? Like, first of all, like if you are, if you're feeling comfortable with the material that I am sharing, uh, there will be a lot of projects on Kaggle available. But for starters, I would say, whatever the notebooks I am sharing, you should go through those and try to play with those models, change some parameters here and there, and try to see how it makes a difference and so on. But if you are looking for you know full on projects, uh, then there are a lot of projects available on Kaggle, and online you can find a lot. So even yeah, that's it. Like, but I mean, if you give more specifics about what are the projects that you're looking on, then I can suggest better. Okay. So yeah, that's it. Mm, right. Okay.